Hello and welcome back to ST118 Statistics and Applications Session 4. In this session, we want to go into the specifics of one population hypothesis test. In the earlier video, we discussed the general structure and components that are applicable to all hypothesis tests in statistics. Of course, those will apply here as well. But what we want to focus on in this video is the specifics for one population mean test. Right? So the calculation steps that are unique, the kinds of calculations done that are unique to one population means test, and I guess the most important aspect of it is when do we use it? Right? In what situations do we use it? Let's start with that. So one population mean test. Okay, so application areas. Calculations and specifics. All right, let's start with that. Remember that this is hypothesis test. And so in all hypothesis tests, the goal is to find the mean, right? Yeah, so it's to find the mean, or because it is hypothesis test and not confidence interval, we're trying to categorize the mean. Is the mean greater than some number or smaller than some number? The number is called the hypothesized mean, right? So let's start with the application areas. So because it is one population mean that is not known, mu itself is not known, and we're not trying to find to the last decimal place or even one decimal place what is the value of mu. We're trying to categorize it. So we need to come up with a sort of a delimiter, a boundary, a number. The number is called the hypothesized mean. And mathematically speaking, that's what we want to do. But in real life, it's the reverse. We encounter these situations first. Then we think about how to proceed, and that's why we come up with the need to perform one population mean test. So one example is assessment. Anytime you need to make assessment, all right, you need to assess whether a person, an entity, and a product, an item is good or bad, right? So it's a good bad situation. Good bad, is it good, is it bad? And you need to make a so-called objective, right, statistical assessment. Is this employee performing well? That's an assessment, right? So annual assessment. Is this company doing well? Right. So good or bad? Is it good or bad? Is it good? So always can turn into a question, right? So you want to make a statement. Somebody makes a statement. This company is good. This product is good. This car is very fuel efficient. Now, of course, somebody says that you don't have to believe, and so you want to find data support. You want to assess, is this good or bad, right? So in those situations, you want to consider using one population mean test. And another big area is judgment, right? Judgment is a bit like the legal sense, conclude, right? Make a judgment about win and lose. Right? Who won? Who lost? Which one wins? Which one loses? Right? So if you need to decide on this kind of outcome, then you want to think about using one population mean test. So for example, we want to judge whether this athlete qualifies for a marathon run or elite marathon run, right? So how's the timing? Okay, first timing, second timing, last year's first timing, second timing. You use sample to judge whether this athlete's population of marathon runs. That means if if the if that particular athlete runs infinite number of marathons, which is impossible for any human, but we can think about it, right? And the actual timings that we capture, even including last year's marathon runs for this particular athlete, are samples of his or her performances, right, in this whole big infinite population of marathon run timings. So populations in the statistic sense is always a bag of numbers. So judgment, we judge, yes, this athlete qualifies, no, this athlete doesn't. So what's a useful tool? One population mean test, right? You cannot be looking at the final marathon run because maybe that run the athlete didn't perform well, but there has been a few samples of his or her runs in the past, and if you consider them overall as a sample size of 4, let's say, right, then you do a one population mean test to judge whether the athlete qualifies or doesn't qualify, win or lose, right? Gets first prize or not, pass or fail, right? So in some sense, it's good or bad, but there is a consequence to it. So that is another category, and the third category I can offer you is decision making, right? So when you need to decide, when you need to decide to take action, then you want to consider one population mean test, right? So do or don't do. Invest or don't invest, right? I only invest, for example, if a particular stock has proven ROI of 5% or more, let's say, right? So now this particular stock X, is stock X worthy of my investment? Does it qualify? Should I invest in it? Should I do this investment or not? Then let me sample, right? ROI for this stock. What's the ROI per dollar invested, let's say, right? And of course, in finance, in stock market, sampling is quite easy to obtain, right? In fact, you have to sample from the sample because the sample size that you download from any freely available database historically is quite large, right? Just look at Yahoo Finance. So when you download the sample size itself is very huge. You can download 1,000 day sample. So it's still too large. Then you want to randomly sample from this sample. That's also okay, right? And so when you do that, you want to use those samples to test whether the annual return, the population mean return, mean ROI, whether it's per dollar or per year basis, for this stock X is above 5%, right? So if it is above, then I decide to invest. I do it. Otherwise, I don't. So that when you do it this way, you kind of detach the emotion. Oh, this stock is what my parents love to invest in. So I really want to, but it's only 3.5% ROI, right? Something like that. So you tend to be able to make a more so-called objective decision, right? So that's the one big category. All these dots are big categories. That means you don't just see it in finance, in stock, in sports, right? You certainly see this in HR, in people, right? In any race, in any competition, assessment. Even if there's no competition, you do make assessments. Not necessarily trying to make any decision, but just trying to decide if this person, this performance, this entity, this product, right, is good or bad, right? So these are big action areas on your part. You, the person consuming statistics. You need to do this. Normally, you guess and check. You just do it, like what Nike says, without proof, without data. But now that you are wiser, you are enlightened with the help of statistics, then these are the areas I'm now prompting you to link these areas that whenever you encounter them, you want to think about one population means. Right? Earlier on, you haven't built up this association, this chain reaction that, oh, I need to make an assessment on this group of people. Okay, let me just guess. He looks nice, so I think it's good. That has been your way. But now I hope you are more enlightened. This spider sense tinkles, right? Whenever you need to make this assessment, you say, yeah, I thought that was one of the categories mentioned in Chinchika's video, right? So let me apply one population instance. So I hope you build up this association so that you can initiate using it rather than being told, hey, this is homework assignment, use one population mean test to do it. Because the one saying this is the one that is more objective, is the one that is wiser, is the one that can actively apply a very systematic, mathematically based, I was going to say scientifically based, but we're not doing science here, right? We're doing mathematics, which is even more fundamental than science, to make sure our action, right, our judgment, our assessment, our decision making, they are all based on quote and unquote cold-blooded data rather than being tainted by our feel, our emotions. Sometimes that feel, that emotions, they are good. I'm not saying it's bad in that sense. I'm saying that we at least want the reference first, right? We want the so-called objective consultant, which is statistics, which is one population mean test, who says, oh, this stock is good, right, based on data. But you can veto it. You are the president of the United States, right? You can veto that recommendation. One population mean test says the judgment is this athlete wins, but there's no but because athlete is a race, right? However, you can say, let's check whether the athlete passed the drug test, right? Did the athlete take any, booster drug or whatever, right? That is flouting the rules. You can make better judgment by being supported by statistics. In particular, in our discussion today, one population instance. Okay, so these are the application areas. Okay, specific calculations. And by that, I want to just quickly do a recollection. Right, so recall, because I think the graphs are very nice. So I'm going to do a quick recollection of them. That the three cases, isn't it? Yeah, the three cases of hypothesis statements, okay, where we remember this is X bar, all right? X bar is like almost always going to be looking very nice, right? Nice in the bell curve sense, regardless of X, the parent distribution that we actually are trying to measure. So in one instance, right, we said that the H naught was mu greater equal to 10. Is the mean temperature, we don't need to say, or rather layman's way, we don't say population mean temperature, right? Because seldom will people say that unless they fail their statistics test and they keep wanting to remind themselves. So normally people will just say, the average temperature is feeling quite low. I think this 10 was not about temperature, but more about mobile plans, right? Mobile payment. I think this new mobile competitor is selling very cheap plans. I think average monthly bill is less than $10, cheap in that sense. Yeah, cheap, right? So we were saying that. And then we were talking about really the temperature. Recently it has been really hot, right? Maybe it's just one day very hot. Then people will say, it has always been very hot. So sometimes people will just exaggerate, right? And when we say that, then the person will claim without proof that mean temperature, right, it has been very hot. Let's say the average temperature must be, I don't know, 37 degrees, right? Because it's hotter than my body, so it has to be 38 degrees, 39 degrees. So let's say it's greater than 35. That's assertion without proof. So we put in each one. And of course, another example quickly was the two-tail case where we were saying something like we asserted that this car is efficient. It is consuming about 100 liters per week. It's not efficient. That's not efficient. So we convert that statement to what do you mean by efficient or not efficient? 100 liters per week. That's like a lot, not a lot, kind of a neutral statement, right? So when we need to say a lot means at least that amount, isn't it? So it's slightly one of these. But when we say this, maybe it's more like a salesman trying to sell this. This car is quite okay, quite okay with the petrol consumption. It's taking about 100 liters per week. Maybe it's not a good number, but certainly salesperson doesn't want to advertise something that is bad, right? So it's doing about 100 liters per week from a few of my customers who bought this car. So number one, saying this 100 liters per week is not that bad. Number two, saying that, hey, you know what? A few of my customers already bought this car, right? Psychologically, it has some effect, right, on you, the potential customer. Okay, so the right hand side numbers, they're kind of like magically appearing, and we call them the hypothesized mean. And we call that throughout our one population means test, we always right, we always assume that H0 is true. We assume that H0 is true. In particular, H0 is true means the mu takes up the equal sign value, 10, 35, 100. Okay, so throughout here, we'll just take it as alpha equals to 5%. Is that okay? All right. So we were saying, let's finish up the picture, that this is the alpha. So alpha equals to 5%. And the right tail test, and of course I go by the H1's little sign here. It's not really mathematical, but this greater than sign seems to be an arrow pointing to the right, so it is right tail. But it works. You can sometimes use whatever observations you personally notice to try to reinforce your own learning, right? It's so long as you know what's the right thing to write down and say. Okay, so here it's a two-tail test, given that alpha is 5%, so we got to split alpha. So one side is half alpha, 2.5%, and the other side is also half alpha, 2.5%. Okay, now what we like to do is to, of course, let's say pick one of them and consider the test statistic. Right? So the test statistic is basically converting the summaries of sample data. What are summaries of sample data? The descriptives of sample data like X bar and S, and also N, the sample size. Combine these three numbers into one real number, right? That is called the T test statistic, if you choose the T distribution. So we'll just illustrate using the T distribution as I, explained earlier on in other videos. We encounter T a lot more frequently in real life, and more because T is a mathematical construction. T distribution, right? It's constructed mathematically. It doesn't exist in real life, but it exists mathematically. especially in this case where we are doing calculation, we're in the mathematical space, we're no longer in reality, right? We're in this mathematical realm, and this realm is where we don't have good knowledge of sigma. Okay, we don't have good knowledge of sigma. So I explained earlier on that we don't have good knowledge in double sense. That means we are suffering from double whammy. Number one, we are using S, the sample standard deviation, to point estimate sigma. So that point estimation already includes some error, sometimes big, sometimes small. Although the chance of large error is very small, it can nevertheless occur. So that's one layer of uncertainty. Secondly, especially when n is small, we know that S itself is all the more a very badly computed number in the first place, right? So when n is small, S itself, S the number itself, has very low fidelity. It's like taking a camera with 640 pixel by 320 pixel. The picture that comes out is either very tiny, or if you enlarge it, it'll be very pixelated, right? Very, very low in fidelity. And so is the case for the case when n is small. So when n is small, the value of S itself, we know is already unreliable. We use this unreliable number to estimate, right, sigma, and then treat it as if it is sigma. So our estimated value for sigma is even more unreliable. So T is created to compensate for all these with a reduction in degree of freedom and some modification in the tails. So the details, you can read about them if you're interested, but we're just going to continue our video here. All right, I'm just going to write across those alpha wordings because you already know them. Now, of course, the mean, or rather the hypothesized mean, that we treat as mu, right, throughout our hypothesis test, right? Remember, H0 is assumed to be true until proven otherwise by data. So the mean always translates to a 0t. And then the scale is not necessarily 1-to-1. It cannot be 1-to-1. And then we, of course, will establish the boundaries here. We call the critical value, right? So the boundaries on t, on the t-axis, the value on the t-axis is called the critical value. Right? So beyond, whenever the test statistic ends up to the, in the tail area, we call that the rejection region. Right? So in this case, the rejection region is to the left because it's TC or smaller in this case. So rejection region. Okay. And here we have two TCs. Typically, if we keep TC as a positive value, then we can call this the minus TC and the plus TC. Right. And we have two rejection regions. The left rejection region and the right rejection region. Rejection of what? Rejection of the H0. That's right. Okay, so rejection region. Okay, right. So let's consider the third case here, right? And by filling in some numbers, so mu naught is 100. N is, for example, 64. Let's assume that X bar from the sample is 105. Of course, in real life, you will get a file of all the raw numbers. Then you easily take the average, right? And also, you easily calculate the sample standard deviation. There are many ready commands for you to run over all the numbers and then to churn out the sample standard deviation this way. So we want to convert, or rather combine, these numbers into the test statistic. So what is the test statistic? The test statistic is going to be T. If it is Z distribution, then we will use Z. But fortunately, the formula is the same. We will be using x bar minus mu supposedly, but mu is equal to mu naught is equal to 100, right, over S over square root. Of course, whenever we have knowledge of sigma, we will use sigma. Then we can use Z distribution. But right now, we stick with T first. Equal, and that is going to be, right, that means our t-test statistic is going to be, let's repeat the alpha here also. Okay, t is going to be 105 minus 100 over 12 over square root 64. Did I get that right? So that's 3.3333. Okay. And we can calculate our TC here. TC, it's the boundary of the significance region. If in the two-tailed case, it's the half alpha boundary. Of course, the other side of the region is the minus infinity and the plus infinity, which we don't have to mention. So if you calculate the TC, it is, if you get what I get, it should be 1.9983. Of course, there's a degree of freedom here. It is n minus 1, it is 63. Right? So you need to feed in the degree of freedom for t in order to get the boundary. Okay, so if we enlarge the graph a little bit, so x bar, do a nice bell curve, I hope. Freehand, all right, not bad. Okay, and we can write down 100 here. And the 1.9983 boundary doesn't lie on the x bar axis. So be very careful, right? What we want to draw, however, is the alpha. Half alpha, right? Half alpha. Okay. And, oops, it's not looking very symmetrical. I'm not drawing exact to scale diagram, but nevertheless, it should look, hopefully, as accurate as possible, especially the important markers. Like, for example, in this case, the 0 must align with 100, the hypothesized mean, because we do know it, right? The rest, if it's slanted a bit, I think you wouldn't mind, because it's not distorting all the known facts too much. Maybe a little bit not annoying, but it's not wrong. Here's where we can now mark the TC, right? TC is 1.9983, and here is negative 1.9983. Is that okay? All right. Okay, and then we have the new number here, right? So far we have duplicated the entire thing and enlarged here, but we have a new number, 3.3333. And obviously it is on the positive side, and obviously it's on the right of 1.9983, to the right of it. Yeah, and what's going to happen is that we will try to put it inside. Now, obviously, I've got to draw way to the right, but I'd run out of space. So I'm just going to put here. So it's like a Google pin on the Google map, right? So it's like a Google pin. Yes, it's on the map, but my map is a one-dimensional line. Yeah. So it is this point that is marking the 3.3333. T equals to this. So this Google pin is going to induce an area towards the nearest infinity, that's our p over 2. So this area is our p-value over 2. Half p-value, that is, right? So this half p-value, if you use the t.dist in Excel or pt in R, or CDF, or 1 minus CDF, 1 minus CDF. CDF is on the left side. In SciPy stats in Python, you should be able to find that this half p-value is 0.00072. So it's very, very tiny. So this implies that p itself is 2 times half p-value is going to be 0.001441. It's already very tiny, so you can just put 001 because it's already less than 1%. And it literally means any decent, valid, reasonable alpha you pick, anyone picks, we will reject H0, right? So in this case, we will readily reject H0. So let's write that down. So remember, we have to times 2 because there is as if another virtual Google pin here, which we are not going to draw, but there will be another region that's incurred here. So it's not visible in that sense because it's not really incurred. It's not really an event that occurred. The event that occurred was this pin, right? Because clearly it is a result from the observed sample descriptives. So definitely that's fact. That's happening, already happened. So that's what we have observed, and more extreme versions of what we have observed, right? So is it rare that we see this event? Very rare, because the bulk of events, if we randomly select data, anyhow pick, by chance you may pick a large value, but most of the time, right, you should be getting those in the middle. That's the meaning of this part bulging up, high frequency of occurrences. Now, after picking 64 measurements, you found an average that is so large, and the chance of this event occurring, because we want to give it an area, right? Because you don't have area, you don't have probability. So we want to give it an area. So the area cannot be this side, it has to be this side. So this or more rarer events altogether makes up 0.00072, or even if we double it to make sure that we can compare with alpha, it is only 0.0014. So is that rare? And we agree that 5% or less, right, is less, is rare. That's the meaning of alpha. Anything that's 5% or less is rare. So a rare event has happened. Now you got to be a bit exaggerated in your mind. A rare event is not that, okay, so what? You're just being lucky. You cannot react that way. You have to react in a logical way. A rare event, okay, a rare event is like, it's like meteorite striking Earth. It's like Singapore having earthquake. It's like impossible thing, or so far what we thought was impossible is now possible. It's now seen. Why do we say we have seen it? Because this is the event that we have observed. For otherwise, we would have drawn this Google pin. We would have obtained this test statistic. So test statistic is fact. It's something that has happened. And how can a rare event to be observed so readily, especially when we randomly pick up the measurements? So it's not about our luck, right? It's about the logic. So the logic is most likely the 100 is wrong. It possibly could have been 120, 115, or even 108, 104, or 105. That's why when we randomly pick 64 measurements, which is not little, right? Our average is off 100. And because of the standard deviation, it is very off 100, not just a little bit off 100. If the standard deviation is very large, like 50, right? That means the curve is very, very flat. Then, of course, there's good chance that you also observe something that is 105, 108, 110 even, and there's nothing wrong or rare about that, right? So that's why we say this is a big deal, right? So hence we are supposed to reject H naught. Of course, you don't go through this thinking, right? This elaborate thinking all the time when you do statistics. What you do is you just procedurally, right, compare p-value with alpha and say that since p-value, which is this number, is less than alpha, which is 0.05, right, 001, this is 1 0, this is 2 zeros, we reject H naught and conclude the statement made by H1, right, the one that hasn't been rejected, right? So conclude that the population mean, what was that? Petrol consumption for the car is not 100 liters per week at 5% significance level. Right? Nothing more, nothing less. Exactly what fact we have gathered and what conclusion we can derive from theory, we are stating that now. Now, when we say not, we got to mean that, right? We cannot change it to is less than 100 or more than 100 liters per week because that's not what H1 is saying. From here, there is an indication that likely, right? Likely, the population mean petrol consumption is higher than 100. Okay, so but you cannot draw conclusion from here. Why? Because we started off setting up the so-called battle scene like this with two-sided rejection region. So when you sample, your Google pin for this time ends up to be here. But if you do it again, it could have been here, right? It could have been on the left side. So we are not, I mean, maybe not for this case because consumption high is consumption high, right? A car getting older, therefore consumption is higher, less efficient, and it can only get worse. It probably wouldn't suddenly become very efficient and then not efficient again. Fair enough. But I'm just saying that for other cases, when you set up to do two-tail test, you just simply, depending on your luck, your sample may be here, your sample may be here. So you cannot be certain just because this time round the Google pin lands up on the right side. Okay, if you like, you can change it into the one-tail test and then retest again. That's fine. Okay, but if you did write it as a two-tail test, then your conclusion can only be not equal to. Okay, well, sometimes not equal to 100 could mean it is inferior or it is defective because if we want the car engine performance to be exactly tuned to 100 liters per week consumption, then meeting it statistically is a good thing, and exceeding or being lesser is not a good thing. That means more efficient or less efficient is not a good thing. Or rather, this is not really about efficiency now, it's more about consumption rate. It could be spending. Spending, or if you're a private hire car driver, you should be on the roads consuming, instead of kilometers, we use petrol consumption as a proxy measure of how hardworking you have been in the past week. So you ought to have consumed 100 liters. Okay, if you consumed more, no good. But I earn more. But then maybe your family, your wife, your children might be saying, but but then you're hurting your health, right? And you're spending less time with us, something like that. So it's overall not a good thing. If you are consuming lesser than 100 liters per week, not a good thing because you are bringing in less revenue, right? So too much consumption, too little consumption, no good. So there can be situations when maybe making an assessment of how you have been performing in the past week or past weeks. You want to rate yourself, right? How have I been doing? Okay, because doing too much, no good. Doing too little, no good. I think if I set a target of consuming 100 liters per week, I can budget the petrol charges, the rental charges, then I can do my financing and everything, right? So that's a little business for myself, even for each private hire driver. Okay, so that's one example. Now, of course, all other examples are sharing similar thing. You want to calculate using this formula, get the Google pin, drop it down, and done. But there's one specific calculation or category of one population mean test that I want to share with you. And it is, wrong side. And that is called the proportion test. So I want to talk about proportion test with you because is there a need for because very useful test and frequently encountered situations. All right, and that's why it's useful. And also mathematically a little bit less obvious and tricky. So I want to discuss maybe briefly about it. You have most of the components of and structure to understand the general body of the test. So I just want to sort of give an example and then illustrate, right, the tricky parts and application part for this. Now, what is meant by proportion test is that the mu is the population proportion. Okay, the word proportion is frequently almost used in a standard manner across textbooks and publications and journals to mean the fraction, right? The fraction. Population proportion or population of fraction that matches criteria, sort of like versus the rest which don't match. So it's a binary division. All right, so it's like you have a measurement that is 0 or 1. So in this population, population contains zeros and ones only. All right, remember our population. Our population is a kind of a bag of numbers, right? A big set of many measurements, and all measurements are converted to numbers, and that's why we have calculations, and that's why computers can come in, and that's why AI can number crunch. Okay, in this proportion test scenario, or rather when in these scenarios, we're talking about a population, a set of numbers that contain only zeros and ones. Only zeros and ones. Where do we see them? For example, if you talk about a city, right, of say easily 10 million people, right? what is the population proportion of people who own a car, at least one car? Okay, so that's yes or no. Whether a person owns a car, yes, so you put a 1. If the person doesn't own a car, put a no. So a person who owns 5 cars, you put a 1. 10 cars, you still put a 1, right? So you want to convert or state your question, your measurement, in a way that results in true or false, which is common, right? Which is very easy to formulate, and which is why we encounter very frequently. So because this is usually a beginning, and sometimes having detailed counts is either number 1 impossible, number 2 very expensive, number 3 very hard to get accuracy. That means you may get some numbers, but you highly doubt those numbers are very accurate. So it's like a very inefficient set of data that even if you obtained, you cannot trust it wholeheartedly to do your management actions or product rollout or marketing campaigns or whatever it is, right? So, but then yes or no, zeros and ones, it somehow is feels more reliable, right? That if a person who hires a car to drive as a private hire driver, seems like the person is always sitting in a car, but the person is not owning a car, so 0. But then the person is always driving a car. No. We want to know the proportion of people owning a car as a sort of a proxy indicator of their financial ability, something like that. Okay, good. So that's a very clear criteria to measure a person into, or rather categorize a person into either 0 or 1. Okay, so in our example, so maybe we can give a more concrete numerical example. So let example, let mu be population proportion. So if you haven't associated or internalized the word proportion, think of it as fraction, right? The population fraction, the overall fraction, right? Overall fraction of people in this city who owns car or cars. So it's a yes or no. So the population is either 0 or 1, but mu itself is the average of zeros and ones. So the average of zeros and ones can be a number between 0 to 1. Correct or not? Yeah. So if you count all the zeros and count all the ones and you add them all up and you divide by the number of numbers, that's averaging, and you average up all the zeros and ones, you end up getting the population proportion. So mu, in a way, is correctly saying the average of all the zeros and ones. Okay, so let me just add that in. And so this implies that mu is equal to average of these zeros and ones. And you reason that out. Yeah. So if you can reason that out, then basically there's no difference. It's just one population mean test. Right? Why I want to point this out is because some textbooks, they call mu maybe rho, maybe p, maybe a different number. They will start off like that, so as to even give a sense that it is a different test. But actually it is the same. The same procedure, the same specifics, the same calculations and everything is what I'm trying to say. Everything is the same, except one thing. Except typically the sample size is very large. Okay, so typically the sample size, so number 1, population is not normal. It's called Bernoulli distribution. It's either 0 or 1. Okay, so it's called Bernoulli, and we know that it is not normal. Now, remember, if it is not normal, then our sampling distribution of sample mean cannot be a t distribution. However, however, the n is very, very large, like in the hundreds or even in the thousands. So much so that CLT, more than CLT, so CLT kicks in and CLT says the sampling distribution of sample mean will be normal. And it is so normal that because n is so large that we will use Z distribution instead. We can use Z distribution. Now, if you use T distribution, you're going to need an n, right? You're going to need a degree of freedom, n minus 1. Same as before, right? So in our test statistic, we will need a degree of freedom. In our critical value, we'll need n minus 1, but our n is so large that it's in the hundreds or thousands, and all the numbers that you get for TC, for p-value, for whatever, will be very, very close to the numbers you get if you just use Z. So we will use just Z. So that's the reason why. Okay, but that's not the tricky part. Or rather, can use Z. So sometimes you do see textbooks saying by CLT we use Z here, right? And that's the reason why, because n is not just large, not just 30, 50, 40, but very large, right? Like in the hundreds or even 2,000 or even something like that. More because zeros and ones are cheaper to get. People are more, even if you interview, people are more ready to say, yes, I have a car. I won't tell you, I lost count how many cars I had, something like that, right? I have a car, right? I own a car. Or no, I don't, right? I don't own a car, right? So it's very cheap and efficient to get. So the sample size tends to be large in real life, in practice. Okay, so let's carry on with our example here. And we assert, right? We claim that the claim is, let's just go direct to the claim. The claim is more than half of people own cars. Okay, so what that means is H naught is mu less than equal to 0.5 H1, because the claim is more than half, right? Okay, so the claim goes to H1 like this. And we know that mu naught is 0.5. N has to be large. So we have to ask 1600. And that's because you're also, in practice, cheap to obtain a yes/no answer, right? Because if you ask several questions, some of you who have done survey before, right? People at first will answer, sorry, can I know your brief name? Oh, I'm John, I'm Tom, right? So people answer. But by the time we come to the fifth question, people start to say, how many more questions do you have? I have to go, right? Or can I know your age, please? Can we skip that question? No, so they answer everything, but except one or two, which become, leaky or empty fields in your internal calculations later on. So should you discard that entire set or not? So it becomes very expensive to obtain fully qualified set of answers. But yes, no, very easy, cheap. All right, cheaper. Okay, so we have 1600. We will we will ask 1600 people, and the count of those who say yes with car, Let's put it at 837. And we set an alpha to 10%. So far, okay? All right. Now, of course, all these will be what you call that? Will be numbers in real life. We'll have 1600 rows in Excel, right? Or in Pandas data frame, right? And so on. Okay, and what do we want? We want to calculate the X bar first of all. Where's my X bar? Okay. X bar is the average of all the yeses and nos, right? The nos are the zeros, the yeses are the ones. That means there are 837 yes and the rest are nos. The nos are zeros. Zeros you add up to zero, right? So in other words, we have 837 plus the rest of the zeros divided by the total number of numbers. So our X bar is going to be 837 divided by 1600. Okay, so that is going to be 0.523125. We better keep a few more digits, all right, so as not to cancel out. Now, here we are approaching closer and closer to the tricky part. Where's the tricky part? Okay, the tricky part is when we use Z, we need to know a little bit, right, about the what we call that, the sigma. Okay, where is the sigma? Where's the sigma? Where's the sigma? Well, the sigma is, in this case, found by the knowledge of the shape of the population X. The shape of the population X, as I mentioned earlier on, is Bernoulli, right? So, because population shape is Bernoulli, we the sigma is related to mu. Okay, so this is the main dish to mu. Now, what's the big deal here? The big deal here is that in normal distribution, mu and sigma, they are not related. You can change mu, you can know about mu without knowing sigma, and so on and so forth. All right. But for Bernoulli, and actually for many distributions, normal distribution is the one that's not normal or abnormal. I don't know why they call it normal. Normal distribution is very weird because you can know about mu or change mu and leave sigma alone. Right? It's like the fatness of the shape of the bell curve is not changed, but you shift the entire mountain to the left and right so that the sigma is preserved and you change mu. Or the width of the bell curve is something that you don't know, but you can know the position of the bell curve, the center of gravity, the mu itself, very clearly. Right? So these are like independent numbers. Not so for Bernoulli distribution. In fact, for many distributions like exponential distributions, binomial distributions, many distributions, the mean and the standard deviation, they are closely related. There's a formula, there's a bridge linking from one to the other. Therefore, if you know one, you can kind of like reverse engineer to know the other. Right now, so it is like almost impossible to say for Poisson distribution, I know the mean arrival rate, but I don't know the standard deviation. But you can just calculate, right? Yeah, so you can just calculate it. For exponential distribution, I know the mean of the exponential distribution, but I don't know the standard deviation. But the standard deviation is just exactly the mean, you know. So that's the peculiarity of that. Now, for population means test, here's where the logic, or rather the circular logic comes in, right? We don't know the sigma, but we need to know the sigma to calculate the z. How do we go about it? What's the value of sigma? It is all right. So we do know that sigma is equal to the population proportion times 1 minus population proportion and then square root, or the other way around. The variance is p times 1 minus p. Okay, so that is the bridge that connects mu. This is just mu, right? Some textbooks use the p here, right? So if you know mu, you can obtain sigma. But what is mu? Because we are testing mu, right? We are testing mu. So how do we know mu? If we don't know mu, we don't know sigma. And so we cannot calculate the z test statistics. Then what do you mean by can use z, right? We simply cannot use that. Can. Why? Because remember that throughout the hypothesis test, and this is a hypothesis test, we assume H naught to be true. In particular, whenever we need to know mu and we don't know, we just assume mu is 0.5. You see? So that's why we can untie the tie, right? And so this means that since H naught is assumed true, we get sigma is equal to square root of 0.5 times 1 minus 0.5, which means is 0.5 square, then take the square root. So sigma is perfectly 0.5. But of course, it's not going to be a perfect 0.5 if you change it to 0.4, 0.3, and something else. But you know the logic and the formula now, okay? So we can now obtain the sigma very easily. From here on, the t is very easily obtained, right? So x bar minus mu naught, sorry, not the t, the z is equal to sigma over square root n, right? So over here we can get okay. Z is equal to 0.535125 minus 0.5, right, over our sigma, which is 0.5 over square root of 1600. Now that is a nice number for square root. And if my calculation is correct, and if it is not correct, then you correct it, but you at least already know the logic behind. So 1.85. So what we're going to do is to sketch a curve quickly. Right. So first is x bar, of course. X bar is the values that we can observe, can calculate, and it will be centered at 0.5. Now the x bar, right, is not based on measurements. It's based on the averages of zeros and ones. Right? So we're gonna have a bell curve, and it starts come down. Okay, like this. It is a one-tail test on the right side, so we're gonna have a 10% over here. Okay, so that's our alpha. Okay, by now you know the light green is 10%. Okay, and we want to have a z-axis. Okay, obviously every unit scale on the x bar is different because one unit is already done, right? One unit you are like in the 100% already. So in fact, one unit is yeah, because it's 0.5, right? So 1 unit is you're done. So not possible. You have to oops, sorry, it's divided by 1600. Huh? So 1 unit is very tiny little steps, but the Z is a different story. Z is on its own. 3 units and you're out, or plus minus 3 and beyond, it's outlier. Okay, so this maps to 0 just like the T case, and we want to obtain this ZC, the critical value. Either that or you obtain the p-value. We do both, right? So ZC, you can use the nom.inf in Excel, all right, and Qt or qnorm, sorry, in R to obtain the necessary Z value. Okay. And at this point, my calculation shows that this is actually 2.2816. Don't know what you have. And already it is clear, right? So you can either calculate this and then compare. Since the test statistic 1.85, it's somewhere here, right? So the Google pin will fall right here. 1.85. Since the test statistic 1.85 is less than the ZC, we do not reject. Okay. Or we calculate the p-value. The p-value is going to be starting from the test statistic and then all the areas towards the tails infinity. In this case, our tails infinity is in the positive side, so towards positive infinity. Okay, so what do we get? Our p-value, all right, is 0. Okay, so the p-value here that I get is a little bit strange. So I checked again and I realized that I wrote a little bit wrongly. That's not 2.28, but 1.2816. Sorry about that. Okay, so it's 1.2816. Then obviously my p-value here is all the more incorrectly positioned. So let me make them disappear. Make them disappear in a way that is really magical. So the calculation of 1.85 is correct, but on the diagram it needs a little bit of an update because it's not just because it's not drawn to scale, but relative position based on the facts that we have calculated is not quite right. So we need to get it straightened up. Fortunately, it's a very simple thing. Okay, so we get 1.28, and the t-test statistic, the Google pin, will have to land here, right, to make the 1.85 correct. So from here, our p-value will be this part, right? So I'm going to emphasize this orange region and emphasize this green region. Okay, so the p-value that I get, 0.032157. Okay, all right. So for the decimal places of p-value, very good enough for many practical application purposes. Okay. So what are we going to do? We can use the p-value to compare with the alpha, or, and in this case we don't times 2, we just directly calculate. or we can use the test statistic to compare with the critical value or values, right? So in this case, both are fine. I highly encourage you to stick to p-value. P-values are lesser used in the earlier days. Earlier means in the 70s, 80s, 90s, because of the difficulty to calculate the p-value, even with calculators, right? Much less to say without the calculators. So only in advanced calculators, very expensive calculators, you can afford to calculate normal distributions p-value, and sometimes t-distribution p-value. But other than that, it's getting harder and harder, right? But these days, it's very easy to compute them very accurately and quickly. So we can use p-value, which is very convenient to calculate, to produce. So p-value equals to 0.0322. And of course, those of you who have been watching and learning, you realize that this number is in the alpha-ish region, right? That means from 1% to 10%. So better be careful, but no choice. Uh, we are unable to extend this because extending this materially to make sure it's more reliable is going to, you have to change it by the hundreds or the thousands, then you can see something. Adding 10 more, 20 more, 50 more, probably not going to affect the result too much. It will still be in the alpha-ish region. So we stick with this. So since p-value is lesser than our chosen alpha, which is 10%, right? That's why we have to agree on the alpha first. Yeah, we reject H naught and conclude that, conclude what? Since we rejected H naught, we conclude H1, that the population proportion or population fraction of people, of people owning cars is larger than, is larger than 50%, right? At 10% significance level. Okay, so that will be our template conclusion. We have to make this. We have to kind of like state this to summarize everything. But then what, right? As a business person looking at this result, you don't stop there and then hand in the homework. You want to look at it and say it's larger than 50%. Okay, so suppose launching our product or not launching our product depends on whether people can afford or not, and our afford to have a car or not, right? And our, because our product, I don't know, is related to car, um, is about car, is used together with car. I don't know what, right? Maybe it's the car's wireless charger, maybe it's a car leather seat or whatever it is, right? So we need to ensure that more than half the people in this town, in this city, owns a car, right? Then we have a chance to be successful in our product launch. So is it true? And after serving 1,600 people, we get this. But does that mean anything? It's more than half, yes, but it can be due to random fluctuation. Is it sufficient evidence to show that it is definitely more than half? Remember, this is the result for 1,600 people. That's very clear, very truthful, very exact. But this 52.3%, does it extend to the whole city? Or should we just say, or there will be a colleague who says, no, it's just 52.3. This is randomness, right? So who knows? In the next 1,600 people you survey, it might be 47.2, right? Or it may be 40.5, who knows? How can you be so sure? But after this procedure, we are pretty sure. We are pretty sure. Because of this whole procedure, we have a we have selected an alpha of 10%. What does that mean? Alpha means the significance level, I'm sure you know. But alpha also means that the probability of making a type 1 error, probability of making a type 1 error is 10%. The probability of making a type 1 error is that we rejected H naught even, right, when H naught is true, given that H naught is true. So it's a conditional probability. So what does that mean? It means that suppose actually the population of people owning car is 40%, less than 50%. Huh? So H naught then is true, right? Suppose that is the case, right? Then the chance of us thinking wrongly, because we're going to launch a product thinking that the population of people owning cars is 60%, right? So we think wrongly, we launch it. So the chance of making that mistake is alpha. That means 10%. That's the meaning behind. So in other words, if someone is going to say, but you're going to make a mistake, you're going to make a 50% mistake because you think it's more than 50%, but actually it's 30%. You're going to make a 50% mistake. We say no, actually the risk is error controlled, is bound controlled by alpha. Now the meaning of alpha is that suppose H naught is true, but we rejected wrongly, right? So there's a mistake, right, in our conclusion, in our statistical conclusion. What's the chance of making that mistake? That mistake is 10%. Or because we chose it to be 10%. Can we choose it to be smaller? In fact, we can choose it to be as small as 5%, and it's still correct. So we can redo everything with the same number, same statistics, same data set, and the conclusion is still that we reject H naught and launch our product, right? And that mistake chance, because the city actually owns lesser than 50%, less than 50% of people own car, is actually just 5%. So you see that our argument gets very strong support in terms of the logic based on the same data. But if you just do this division, people accuse you that you're making half the chance making mistake. You're going to gamble our company away and all that stuff, right? How are you going to defend yourself? You cannot, right? You're just going to see who is more senior, who has a louder voice. But that's not the way we do arguments in statistics, right? So I hope through this example, you have not just seen another very interesting, or rather mathematically interesting illustration of one population means test and the calculations, but also get a feel of what happens when the population is very non-normal, okay? And what happens when the population's behavior, especially of the standard deviation, sigma, is related to the mean. Then what happens to your calculation steps, along the way. So we have learned how to resolve that and make use of the assumption that H naught is true, right? And finally, when we make a conclusion and the secondary conclusion to take action. So yes, more than 50% of people have cars, so we launch our products. When we take action based on this, that's our secondary conclusion. What kind of risk are we taking in terms of probability of making a mistake? And here the true meaning, right? The true meaning of alpha comes out, and that is helping us to reinforce our decision, right? Of course, nothing is 100% correct, or nothing is 100% wrong. But when we want to talk about an argument, to win an argument, to have greater reliability and confidence in our decision making, we need to understand the meanings behind these numbers, right? Other than and beyond just a homework assignment that is to be handed in for marks. Okay, with that, I thank you very much for your attention, and that will be the end for this video.